Hello, everyone. Good afternoon. This is lecture 20 of PTRE 575. Again, about 10 to go. We should be um, we should be closing module 3 today or the next lecture, and then we are gonna move to module 4, which is gonna be very similar to production engineering. Actually, it's going to be some concepts that you have already seen, most of you, either in production or in fluids, even. And then there is a short one to go for module 5, which is really, again, a production engineering subtopic. And then we are done, basically. We will be having we come back on Tuesday, April 7th. The homework is due on April 6th, the day before, Monday midnight. And I'm really sorry, I forgot it was Easter Monday, but I kind of prefer that I give you the homework. This is an easy homework, and I wanted to get it out of the way and have more time for the last homework. And then because we have a midterm, a homework coming up, and then the final, and the term paper, of course, which I hope that you guys are working on it pretty hard. A few announcements. Well, before I start, are there any questions on the homework? Those are the ones I want to knock out as soon as possible. Okay, if there is no questions, I'm still available by email during the weekend. I don't think I'm going anywhere, so reach out to me if you have any questions, and I should be able to help. Same thing for the TA. I have a little bit of an issue with Authenticate. So if you guys start sending me your drafts, I may not be able to. My old account with LSU is not, with my old LSU email is no longer working. And it's not like I can retrieve, it is not like I can retrieve a password or something through that email. I think the school's contract with Authenticate was terminated. Not UND, the LSU. So I cannot use it, which is quite a bummer because I was using it a lot. I mean, even I remember using it in January. I don't know what happened, but either way, please keep working on the term papers. This is not something that can be done in 2 days. The more you work on it, the better your grade is going to be eventually. That being said, okay, there would be, like I said, another homework, which is going to be on module 4. And then module 5 is going to be a very quick module. We can cover it in like two lectures. So it's no big deal. So we're approaching the end. And I know that several of you guys are taking your senior design classes and are ready to graduate and go out to the world. And I wish you the best. We'll come to that when the time is arriving for the end of the semester. But yeah, last time I think we made it to slide 47 out of 58 on this topic. And oh yeah, this is the one I was gonna say. One of the students, Shamel, told me that this link no longer works, and he was right. I tried to find something equivalent, and there wasn't anything like that. I couldn't find yet. Anything else I could find was related to computational stuff, which are beyond the charter of this class. So I wanted something on the physics of fractal propagation, fractal growth. This is what I was going after. And sadly, it wasn't really, I wasn't able to get something like that. So for now, ignore this slide. And if I find a good video, I will send it by announcement or something. Make the change in the slides and send it by announcement. But yeah, there is nothing really comprehensive on the physics. It's more like either on the computational methods employed, which again we don't do about those in this class. or just like general talks that is more like commercially focused talks. I want something more. It was a very nice one that I had here with Mark McLeod because he was really focusing on the physics and it's stuff that we were like doing in class. But anyway, so let's ignore this slide for now. Now, unconfined compressive strength, UCS test. We talked about the SCB test. And we said that it's a very weird looking test, but it's a very easy to apply equation. Like you need to cut a sample in certain dimensions, but the equation is so, oh, sorry, what did I do? It's so simple, like you see here, that is very, very easy to get. And then you are given a very complicated property of the material, its fracture toughness, which is very useful because you are going to input it into your simulator, let's say, for to run the test and to run the simulations. So it's a very important, very important. The setup you see here is in triaxial loading frame. Better picture is here. Basically, you have a plate, the plate moves up, apply stress. The contact here doesn't move on the top, so stays constant, stays at the same place. If the plate moves up, eventually it will break, it will crack, and then you will have failure. Now, the loading frame has many uses. It's not just the SCB test. The simplest use we are going to see today is something called the UCS test. And that one is fairly simple. You just take a cone, as is a cylindrical plug, basically. You put it in the system. The plate moves up. The contact with the top of the cylinder makes the stress bigger, 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 and eventually it cracks. And when it cracks, it breaks in a certain way, and it gives you an indication, which is what we call the UCS, the unconfined compressive strength of the sample, which we assume to be intact. When we do experiments on small cores, if you remember from geomechanics, we assume that they are intact because otherwise, if you take the core and you put it down, it should fall off, you know? That is an assumption that we make for very big, huge rock masses, okay? If we have a big sample, like a rock as big as this room, or even bigger, we can assume that there is infinite faults in it at infinite orientations with infinite range of properties. And then basically it's not an intact rock. We assume that it doesn't have a cohesive strength at all, like the particles are not connected to each other, effectively speaking. Now we are talking about a very big mass. Now, as a core, though, it can be considered intact. And I don't know any calculations that we do for core scale that are not considering the core scale to be intact. Cemented rocks can bear shear stresses with zero effective lateral stress. Basically, the way that I think it's better if I draw what I'm trying to present here. I have this sample. This is the plate it's sitting on. The plate is slowly moving up at the prescribed rate. We said something like 0.2 inches per minute, like tiny, tiny. You can't even see it with the eye. And the contact is made here. So it's like there is a contact and it will eventually crack. And as you learn from geomechanics, you'll crack something at 60 degrees like that, or like that. What will determine that if it's going to be broken like this or like this is pre-existing fractures inside the sample, like mini cracks, very tiny bit, and heterogeneity. Actually, if you take a sample after it broke and you see the breakage is something like this, if you check it well, and we don't have anyone to show you now, you are gonna see cracks already made like on this direction, on the other direction as well. So it was gonna go either way. What determines which way is basically the pre-existing mini cracks. Now, why do we call it unconfined? I think the compression you understand. The plate moves up, the contact on top stays stationary. Obviously, I have compression in basically, this is Newton's third law. I have compression in the z direction, assuming that the z direction is along the axis through the cone. I have some compression. Now, what do I mean by unconfined? By unconfined, I mean we do not have any confinement, any stress from outside, okay? And because the core is cylindrical, any stress from outside, it wouldn't be in the x and the y direction, but it would be in something acting all around. Basically, I'm doing dots, basically acting inside the plane of the screen. So all around the code, this is gonna be radial stress. The confining stress is basically radial. It's in the radial direction because of the shape of the sample. If it was a square sample or a cubic sample, I would be calling it X and Y. But now because it's cylindrical, it's better I call it radial. Now, UCS is the maximum compressive stress applied in the axial direction, hence sigma ZZ. The rock can hold under unconfined conditions. So if my radial stress is 0, how much sigma ZZ can the rock sustain before it cracks? Axisymmetric tests require rock samples in which the length should be about twice the diameter to minimize shear end effects. So basically, typically we have rock, typically we have, I don't care about the picture right now, I care about the, typically we have samples that are 2 inches long, 1 inch wide, 1 inch diameter. So it satisfies those conditions. If they are too short, we have something called shear end effects. It's like if you take measurements at the close to the edge of the samples when they are being compressed, like I take a measurement here and a measurement here, it doesn't give me the exact right answer. And then if the distance between them is too short, it like interferes with everything, so it gives me misleading answers. And then if the sample is very, very tall, it can bend over, it can backward. So it's sort of like scoliosis of the spine, that if some kids are growing up very fast and their body cannot handle their growth and their spine gets a little bit curved. Similarly like this, you have a very thin but tall sample, it starts bending, you know? So it's not a good idea. You want to have it about 2 inches tall, 1 inch wide. That about the mechanics of the test, but how does it look like on paper in terms of graph? We have something called the Here is from Dr. Espinosa's notes online. Sigma A, he means what we call sigma ZZ. And sigma R, he means what we have sigma RR. Basically, I load the sample with sigma A. Sigma R is always zero, okay? And at some point I get failure. When I get failure, it tells me how much, just before getting failure, how much axial stress could the sample sustain before breaking? And then I create my Moore circle. Now the Moore circle is no longer Cartesian, so it's still sigma 1 and sigma 3. But what is sigma 1? What is the most compressive? Is the axial stress. And what is the least compressive? Is the radial stress. And because the radial stress is zero, the circle is going to be touching the origin. I think I made the same mistake. But yeah, that's how it works. Now I just load it until it breaks. And then basically I get the sigma AA. I measure from the loading frame, I measure how many pound force did it sustain. It sustained 9,000 pound force. Okay. What was the cross-sectional area? What was the diameter of the sample? 1 inch. Okay. So the cross-sectional area was pi times diameter square divided by 4. So it was something like 3.4 divided by 4 is something like 0.9. That means inches squared, I think. And then I basically do that number in pound force divided by inches squared. It's pounds per square inch. That was my sigma A. That's my UCS strength. That's my UCS value. How much I can load the sample before it breaks. So that's the big side of the Moore circle. The small side is zero because the test is unconfined. Okay, UCS test. Any questions on the UCS test before I move on? Okay, from the UCS test, you can make an arrangement where you have something called LVDT, low voltage differential transducer, something like that. So basically, is what I drew last time, 2 lectures ago. You have the plate is moving up, you have the sample on the plate, the contact, everything is fine. But as the plate moves up, there is something here that basically measures displacement. Okay, as the sample moves up, as the plate moves up, the sample gets shorter and shorter. Okay, if you can measure how shorter it becomes, how much it's losing in time, then you can convert that to strain, axial strain, by dividing it with the initial height. So it started from like 2 inches, and now it's, I'm exaggerating, 1.9. Okay, so what is the strain? The strain is 2 minus, the strain is gonna be negative because it's compression. So it's 1.9 minus 2, so minus 0.1 divided by the initial value, which is 2. So it's gonna be basically 0.1 divided by 2. So I believe it's gonna be 0.05, which is something like 5/100ths, which is a pretty high strain, but just making numbers easy here. Okay. So as the sample shrinks, you apply more stress and it keeps shrinking. You apply more stress and it keeps shrinking. Okay. If I plot the value of the middle plot here, it has the axial stress on the vertical axis, how much stress I apply, to the axial strain on the on the horizontal axis. That's how much shrinkage I'm getting. Dimensionless. Basically, that's 0.05, how it changes. And then it's going to be a very weird shape, like the one that Dr. Espinosa put in his notes. Now, if I go there and I say, let me take a part of this line that is straight in the middle, draw a tangent, and calculate the gradient of that. Okay, what would be the gradient? It would be stress divided by strain. Strain is dimensionless, so nothing on the denominator. Stress is PSI, as we said earlier, pounds per square inch. So the gradient is actually the Young's modulus. So that's how I calculate the Young's modulus. These two things I can get from the UCS test, which is very nice because it's a very quick test. It doesn't take a lot of effort. It doesn't need a lot of preparation. And then I can get some very useful information because the Young modulus is another sort of parametric input I can use in my system. Any questions before I move on? Okay. Confined strength with now, now confined. We went from unconfined to confined. What does that mean? Is that now I no longer have sigma RR to be 0. Sigma RR will be a value. I'm going to find a way, don't worry about how, to apply stress confinement. Okay? It's not going to change as I go radially. So as I go radially, it's the same value I'm applying, which is good. However, it's going to change the results. Okay? It's no longer the same, obvious. So in UT, we have some specially designed vessels that we put the sample there and we fill them with water. So you have water around the sample, and then you apply pressure to that water. You basically try to pump more and more water. And then the stress around the sample, the radial stress increases. That's how we apply confining stress. And then you basically measure how much it takes until it cracks. And that's it. The measured peak stress is higher than the peak stress without confining stress. Yeah. So now if I have confinement, I'm going to be finding a bigger value than UCS. I'm expecting actually a much bigger value than UCS. The increment in peak stress depends on the internal frictional strength of the rock. Hence, the maximum shear stress is a function of both the rock's cohesive strength and the effective normal strength, which is basically what holds the fold together, the crack together. Once you overcome that, once the left-hand side, the tau becomes bigger than the right-hand side, which is C sub O, the cohesive strength, plus mu sigma n, then we have failure. Now, the thing is that I'm assuming the code is intact, like I said earlier, so CO is positive. Okay, CO is positive. And then how it breaks? Remember, these are shear failures. Okay, they are not tensile failure. We are going to talk about tests for tensile failures a little bit later today, but or maybe next time. I think it's today. But ultimately, the failure I'm gonna get is basically shear. Okay, but I'm not applying directly a shear stress on the sample. I'm applying axial stress, direct like normal stress on the sample, because I have the sample, core, plate moves up, Newton's third law, So same stress on the other side, which is axial, sigma ZZ or sigma. And then I have some radial. Sigma RR. Now, now, how to say, okay, so I'm applying the stress. Everything that you see there is normal stress. Radial is normal. Axial is normal. But somehow, if I have a pre-existing crack here, what I really care about, this is my crack. There is a force trying to make the crack slip, which is in shear and is denoted by the Greek letter tau. And there is a force that tries to keep it together. Called the normal stress, sigma n. Sometimes we use sigma n. All those are normal. All those are normal stresses, except the tau. Now, the tau is a combination. This tau, it depends on two things. It depends on the axial stress, sigma ZZ, and the confinement stress, sigma RR. Okay, together, they make the shear stress that is applying on the wall, where basically that failure plane that I'm about to create a fracture on, that 60-degree angle. So I'm trying to create a fault there, and then a faulting plane, and there is, I'm applying tau through sigma ZZ and sigma R. And then the force that prevents me from doing that is the sigma n. And once tau overcomes sigma n by this equation here, the left-hand side becoming bigger than the right side, then we have failure. With a linear shear failure criterion, a fracture will ideally form at an angle of 60 degrees from the maximum applied stress. So I believe you learned in geomechanics why is it 60 degrees. And there is an equation that you can see and understand why is it 60 degrees. But that's basically what we expect. Now, this is how it looks like. Remember, green is the unconfined that we had in the previous slide. And now we have confinement. Look at how much higher and bigger blue is from green. And most importantly, I want you to pay attention. I want to draw your attention here. Sigma RR is no longer at zero like before. It's now bigger than zero. So it's a little bit bigger than zero, but look at how much bigger the axial stress became. So look at the difference. What I was saying, excuse me, is what I was saying earlier. You increase it by this much, the radial, the confinement stress. You increase by this much, the axial stress. So a little bit increases in the confinement cause big increases in the confined strength value. It's no longer unconfined. The compressive strength values, how much compression you can handle. This is very, very important because it's a typical rock behavior. I guarantee you that. I did a lot of experiments when I was in Texas. Geomechanics, they had their own labs. So we had to gather the students through like 5 labs. The first lab was UCS test. The second lab was CS test. The third lab was something called Brazilian test. We're gonna go over it. And the fourth and fifth was something similar. So we spend a lot of time with those, like, we spend a lot of time with those setups. And I can attest to that. Like, if you apply a little bit of confinement or more confinement, you get some crazy strengths. Crazy compressive strengths. Any question? Okay, so both the confined compressive strength, I should call it, and the unconfined compressive strength, they are both shear failures, right? And somebody will ask me now, hey, what about tensile? How is it done? And I will say, okay, you're gonna do the Brazilian test for the for the tensile strength. So this is how you're gonna measure it in the lab. You're gonna use the Brazilian test, which is basically the same setup. You're gonna take a sample and put it, again, it's a cylinder, but you're gonna put it lying down. So you're gonna apply compression on the sides of the cylinder. So what is gonna happen is that you have it like this. You apply stress, the plate moves up. I'm applying stress up. So I'm applying compression here and compression here. Single point compression. And then what is gonna happen is that automatically is like pulling the sample like that. And ultimately what will happen is it's gonna lead to a failure at 90-degree angle, something like that. And that would be a tensile failure, a purely tensile failure. And it's a very easy calculation after that. Short cylindrical sample, this one will be 1 inch by 1 inch. So 1 inch tall, 1 inch wide. Or could be even 1.5 inch wide. And takes advantage of the shape of the rock specimen to create tensile stresses with application of a compressive force along the sample diameter. And then you measure the stress at which the stress load, the force at which you break, we call that F max. You divide by pi, you divide by L, and you divide by R, and you have the value of the tensile strength. During Brazilian testing, there is a combined state of stress with compression in the direction of compressive load and tension in the direction of perpendicular to the load diameter. That's what I drew with arrows earlier, basically. You apply compression like this, but you induce tension like this. And the trick here is that you should know that the sample is easier, about 10 times easier, roughly speaking, to break in tension than it is to break in compression. So it will crack first in tension before it goes in compression. And this is what Garneiro was the name of the guy who invented the test. And as you can imagine, he was from Brazil. So they call it the Brazilian. I think he was 29 years old when he invented it. And it was in the 70s. Somebody told me the story about it last summer when I was at ARMA in New Mexico, at the American Rock Mechanics Association Symposium in New Mexico. I was chairing a session, and somebody told me, hey, that session, it was Nicolas Espinosa, who was my original advisor, actually, who is an Argentine guy from the University of Texas, and everybody else was Brazilian. So it was like everybody else was Brazilian, and they knew each other. So it's customary that the session chairs sit with the presenters, and they have breakfast together and everything. to make sure that everything is in order for the session to take place. So I had breakfast with them. And, we were talking. We basically became friends. They were mentioning to me about the story about this test, that there was a church that had to be relocated, as it was, to be lifted up and moved or rotated, something like that. They had to do like a big operation to shift the position of a big historic church. So this test became, it was designed to help measure some stuff that were relevant to this sort of big operation. Yeah, that was a fun day, actually. Anyway, that was one fun day in New Mexico. Something else happened in that session. I don't remember. But I remember we were running late. Like there was people who went by like 5 minutes more than what they should. Like, they give you time for the presentation and then time for the Q&A. And some people went past the time for the Q&A when they were even talking. So we had to go very fast. But yeah, I mean, it was a nice group of people. Nothing against them, of course. Now, uncemented sediment is what I mentioned earlier. Cohesive strength is 0. That means if I put the sample here, it will break. Okay? It won't hold together. So effectively, what I'm saying is that the tensile strength is basically 0. So no tensile strength. Basically 0. And T equal to 0. Now, let me give you some typical values. For gypsum cement, which is hydrated calcium sulfate, that's what the gypsum walls have. That's what they put on a cast, an iron arm cast. Is gypsum, not iron, but you get the idea. The tensile strength of that, also known as plaster of Paris. There is a church in Paris that there is this gypsum bedrock underneath it. That's why they call it you may read some papers that they call it plaster of Paris. They mean the same thing, gypsum. Calcium sulfate with some mixed with water. That has about 300 psi tensile strength. Okay, little bit less than that even. Now, hydrostone cement is stronger and has tensile strength of about 700 psi. This is typical of what you face in the rock. Typical rocks are like 500 to 1,000 psi. So not very different from that hydrostone cement. Now, the thing is that 500 to 1,000 is not that much, okay, compared to if I have compression in situ stress loads like SV, SH max, SH min of 10,000. Do I really care about the 500 psi of tensile strength? Not really. I can basically ignore them. Sometimes it's a good idea to ignore them. Sometimes it's not a good idea to ignore them. And it's very difficult to measure them exact. There is some people that say that some shales, because of the presence of clays, they exhibit very, very high tensile strength values that can go all the way up to 2,500. That case is a very big value and should be considered. But generally speaking, you don't really have to consider those tensile. It could be safe to be neglected. Now, in real life, in classroom setting, this classroom setting, you're gonna ignore it only if I tell you to ignore it. If I don't tell you to ignore it, don't ignore it. Yeah, I mean, it's not an unsafe assumption to sometimes ignore it. Example problem number 2. Determine the tensile strength of a shale sample that displayed a peak load of 470 pound force. The sample diameter is 1 inch and the length, its length is also 1 inch. So very simple calculation. Here, F max is 470 pound force. L is 1 inch. R is 1 inch. What is pi? 3.142. So I do that, and I get something like, by the way, this is radius. R is half an inch, not 1 inch. Diameter is 1 inch. So don't get caught there. It's like 450, 470 divided by pi over 2. 2 goes up, becomes 940. So it's 940 divided by pi. Pi is 3.14. Let's 3.142. Let's just say 3. So let's just say 900 on top and 3 at the bottom. So I'm expecting this T to be around 300 psi. And it's, yeah, there you go. No need for a calculator. If you can round up numbers properly and fast in your head, you can do it. But yeah, pretty simple calculation, nothing fancy, nothing crazy out of it. Okay, now, all those three tests are very important, okay? And they happen they take place in a laboratory setting. Now, the benefit of a laboratory setting is that it's a very controlled environment. Nothing, I control even the temperature. Everything is under my control, and I take care of it. The problem is when those fractures that we induce in the lab, they are what we call toughness-dominated fractures. Okay, I'm applying a stress and the crack happens. I'm applying stress like with basically via toughness. That's how we say it. But in the field, when I do hydraulic fracturing, which is what this class is all about, along with some other stuff in well completions, I'm applying stress using fluids. So those fractures are not toughness dominated, they are fluid driven fractures. So a lot of properties may be different when I calculate them using a toughness dominated measurement. But when I try to apply them into a fluid driven problem, there might be some discrepancy. I need to take account of that. Sometimes I need to be aware of that. Now I understand that designing a test to break a sample using a fluid driven method so that it's more applicable, more analogous to real life scenarios may not be the easiest thing for me to do. But I will say that it can be very useful. It can be still useful. And generally, those tests with toughness dominated fractures, they are basically very, very practical and easy to do. Okay? When I need to use fluid, I need a bigger structure. It's basically field scale test. I need to do it in the field, or if I do it in the lab, I need big devices, different equipment. It's a big, big headache. Oh my God, such a big headache. So we have what we call, we're going to look now at some field scale tests, field scale testing methods. The first we are going to see in slide, what is it, 50 something? In slide 52. It's going to be called a step rate test. And this is a test that you apply, that you have to do in Texas is by state law, in every injection well. Every well that you drill that is expected to act as an injection well, is expected to undergo a step rate test. It's a very simple test. It helps determine the maximum injection pressure. We call that formation parting pressure, which is very similar to fracture initiation pressure. That's when, and also similar to formation breakdown pressure. It's like the pressure at which the formation cracks apart. In a wellbore designed for constant and long-term injection, there is a lot of things. Like when you are injecting through a well, you are subjecting this well in very high pressure. Okay, there is a lot of problems associated with it, like injectivity issues. You need a big compressor to pump these high pressures, but may not be always the case. You may have something called well integrity problems that actually I have articulated quite a bit on those. I used to have a student working on these problems, but also different other issues. So you want to be able to understand that your well is gonna be holding, be able to sustain these high pressures that you are gonna be injecting in. Otherwise, you are not gonna be able to inject anymore. So the step rate test procedure, you isolate the injection zone, you inject fluid at successively higher injection rates, you go up. That's why it's called the step rate test. You go up during equal time intervals, and then rule of thumb, 1 hour for permeabilities less than 5 millidarcy, and 1/4 to half an hour for permeabilities bigger than 10 millidarcies, using an injection rate of 5%, 10%, 20%, 40%, 60%, 80%, and 100% of the expected injection rate. You go up. That's why we call it the step rate test. Some people call it the step down test. We brought the former vice president of engineering for Liberty, Dr. Lynn Wires, 2 years ago to give us a talk. And he called it step down test. It really depends on the method that you are using and where you are doing it. These are Colorado-based people. Very important. We plot the stabilized pressure versus the injection rate for each step. And basically, we are expecting to see a ladder-like, step-like profile. The formation parting pressure is indicated by a slope change. And I'm going to show you what I mean by that. This is the ladder that we are expecting to see. And at some point, you end up losing pressure. That's because the pressure is leaking to the surrounding formation. And as you see here, I don't think you can see where I'm touching, but they just say first step, 2 step, 3 step, 4, 5. That's where, between 4 and 5, that's where you start leaking. It goes down. And yeah, this is basically where you start partitioning your formation. It's like pulling it apart or pushing it apart. The change of slope occurs due to fracturing of the injector and can be interpreted as a change of the skin factor. We're going to talk about those more in Module 4. I mention it now because I know that you already took production, so you know what these words mean. But we're going to see it more in Module 4. And also, these slides are also setting up the stage for Module 4, you know. But yeah, basically, if I plot the pressure versus the rate, I'm going to get 2 lines intersecting at what is called the fracture pressure, a fracture formation partitioning pressure, FPP, not to be confused with formation pore pressure or that we did in advanced drilling or normal drilling, or the fracture propagation pressure that we did in this class. So these are three different things, very close to each other, but they mean different things. So don't confuse the terms. Their values may be similar, but don't confuse them. The step rate test is a required test by some regulatory agencies, like the Texas Railroad Commission, in order to safely produce salt water, avoid fracturing reactivation of neighboring pre-existing faults. This is none other than the problem that we discussed and you guys have seen many times in those classes. That's because wastewater disposal has been linked with induced seismicity quite a bit in several areas. Areas like Fort Worth Basin, but also tectonically relaxed areas where you don't really see a lot of earthquakes, like Oklahoma, Canada, like places where many places where they inject a lot of wastewater, they saw increases in induced seismicity, like elevations that were unnatural. And they originally blamed it on hydraulic fracturing, but it's really on wastewater disposal. Where you have hydraulic fracturing, you have a lot of wastewater disposal. That's because you produce a ton of water that you don't have anything to do with it. Nobody will buy it. There is not much use of it. You might as well inject it, but if you keep injecting for a long time, I found it. I read a book with a lawyer that was accused of drunk driving, and he was talking about his ordeal. And there is a part in the book that is, by the way, a book from 1970s or early 80s, so a long time ago. But there is a section in the book where he described how does the body behave with alcohol. It's very similar, like, it takes alcohol at a certain rate, and it deals with alcohol at a certain rate too. If the first rate outpowers the second, then you are in trouble. Okay, so that basically translates to the dynamics of basically induced seismicity from wastewater disposal. If you inject too fast, more than what the rock can take, because the rock can redistribute the water, the aquifer will redistribute the water in such a way that it minimizes pressure. If you inject too fast and the rock doesn't have the time to do it, the rock will accumulate pressure. So it will create some pressure points. And these pressure points, if they are near at close proximity to a big fault, they can make that fault slip, and then it's registered on the surface as seismic activity. So this is why we do, although there is a lot of regulation on those, we call them class 2 injection wells. There is a lot of regulatory activity on those, and a lot of controversy, because when they do simulations, the simulations don't come close to reality because there is a lot of heterogeneity involved that you don't include in the simulations, and there is a lot of lack of correlation, let's put it this way. And it's very hard to convince people to apply some rules for wastewater disposal when you cannot prove causality. It's like a little bit like how do you call it? It has to be constraints in the volume, injected volume, and constraints on the injected rates. Both of them can cause failure. You may haven't injected a lot, but you injected too fast for some time, so that will cause you failure. Same thing, you may have not injected very fast, but you injected a lot. That can also cause you failure. So it's like a lot of things that can go wrong. The objective is to avoid fracturing of the injector well or damaging the injector well. You may get other kind of damage like cement debonding well before fracturing. There are ongoing efforts to regulate injection of large volumes that may not fracture the injection well, but could reactivate neighboring faults. That's what I was talking about. I have a paper, it's online, wastewater. I recently wrote it. And basically I say, no, there you go. Basically I say in this paper that some failures, the well has some failures before the fault reactivation. So places where you expect to see fault reactivation, you don't see it. Why you don't see it is because another damage happened in the well that you don't know about that absorb that energy that would have otherwise been used to cause failure. And basically, we cannot see the whole thing. Don't worry. But ultimately, it's one reasoning that you can use to explain those lack of correlations. One of those, not everything. Now, unintentional fracturing of the injector can be detrimental to sweep efficiency in EOR and IOR processes if the fracture connects the injectors and producers. However, fractures can be beneficial for sweep efficiency if oriented orthogonally to the sweep direction. And this is basically it's an old story. I believe either 90s or early 2000s, maybe even earlier, maybe late 80s. In Alaska, it's a big conventional hub with a lot of conventional oil fields. And several of those fields are under water flood. It's a good place to do water flood because the permeability is good. So you can really flow from one side of the reservoir to the other and sweep as much oil as you can. Now, what was happening is that they were, when you do a water flood, you really don't want to fracture the well. Okay, you prefer it to be unfractured. So you keep the injection pressures below those fracture pressures or the formation partition pressures. Now in Alaska, they were piping the water for the water flood to the injection wells. So what was happening is that because of the low temperatures, the water was getting colder and colder. And then when you are injecting water, you are injecting cold water in the well. And there were some thermoelastic stresses being induced. And those stresses were lowering the formation, partitioning pressure, or the fracture initiation pressure, whatever you want to use. So it was basically becoming easier for the rock to fracture than with normal temperature. So they thought that they were not fracturing the well, but they were actually fracturing it. And it gave them, it didn't give them a lot of problems in terms of sweep efficiency. It was actually almost a good idea that they fractured. It helped production. But they were getting indications that there were fractures. And they were like, no, we're injecting below the fracture pressure. How do we know that there is a fracture? It's not like the well is going to tell you that there is a fracture. So they did a study. I think they gave money. There was a grant that was awarded for that. I don't remember. They did a study and they found out that there is more, basically, the cold water was lowering the fracture pressures, and they were actually fracturing. Anyway, now, fracture closure pressure estimation, FCP. What about that? While the fracture is still open in an open hole section, fluids in the fracture leak off from both the wellbore and the fracture. A large leak of surface, fracture walls, and well causes a rapid pressure decrease approximately proportional to the square root of shutting time. And you will remember this value, again, this relationship proportional to square root of time from the mud cake estimations from PTRE 411. Is basically, it's similar to Darcy's law, but not exactly that. It's close to that. The rates are quite higher than Darcy flows, from my understanding. But yeah, it's a very, very common relationship that if you see here, you have surface pressure going down, then basically compared to square root of time. And generally, before FCP, it's one trend, and then after FCP, it's, well, the trend changes after FCP. If you measure the slope before, you will get this FCP. Sorry, if you not measure the slope, see where the slope changes, stops being constant. It's where you see here, it says 769 psi. That's when the slope changes. That's what I can't believe I did it again. That's another, that's an important value. That's when the fracture closes. It's about to be the same value. It's expected to be a similar value to this. Time, pressure, goes up, sorry, leak off, drops, FPP, FBP, this is FPP formation, fracture propagation pressure, this is LOP, and then you stop pumping. Go down immediately, like stop pumping immediately, ISIP, instantaneous shut-in pressure, and then level off to FCP. This is what I'm measuring here. This is what we are measuring here. The pressure decrease rate slows down once the fracture closes, leak off just from the well, and departs from a linear trend. That's when the slope changes that I told you. When it changes, that value is expected to be closer to FCP. FCP is the pressure at which this change in leak off regime occurs. If you see that from module 1, fracture closure pressure, FCP, fracture closure in general is interpreted to be approximately equal to the minimum in situ principal stress, which would either be SH mean or normal and strike slip faulting, or SSV or reverse fault. Okay, how fast does a fracture propagate? Okay, we talk about UCS, we talk about compressive strength, we talk about I forgot. We talked about tensile strength. We talked about formation partitioning pressure. We talked about fracture closure pressure. All this stuff, you need them for your simulator, right? Supposedly you are writing a fracture simulator, or you are trying to put together a fracture simulation. You need them. You need all those. You need all those values, but you also need something else, which is, like I said before, how fast does the fracture propagate? And to estimate that in the lab, it's even harder. And we have to visit a paper from 2000 or 2001 by some people that actually I know. Skip verification, show me this paper. Okay. John Holter, Dr. John Holter, used to be like a research assistant, a research associate in the group I used to work for during my master's under Dr. John Olson. John Olson was the department chair, and now he's no longer the department chair, but he used to be my advisor. And Zeno Philip, I believe, he's now with ResFrac, part-time with ResFrac or contracted by ResFrac. He used to work for Pinnacle, I believe, which is like a fracture modeling group in San Francisco that the people from Liberty were working for before they moved on to have their own fracture company. So I think Zeno Philip was doing a PhD under Dr. Olson, and Dr. Holter was helping the process. He was always helping us in the lab, Dr. Holter, and he was a very funny guy, very smart guy. I was very sad to find out he passed away during COVID. He was very good with like hands-on activity. Like he was very, very, very crafty person, he had a very can-do attitude. It was very, 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 very fun person to be around. Anyway, back in those early 2000s, before I made any of those, they came up with a dual torsion test to measure the fracture growth, like subcritical fracture, subcritical crack velocity. And all the money, I think this paper has basically, it describes that process, but it has only like 2 equations in it. Yeah, 2 equations, nothing more. So this is the equation that we really care about, okay? Velocity, propagation velocity is equal to A, Ki, which is the stress intensity factor, not the critical stress, not the fracture toughness, but the critical strength, N, which is the critical fracture index, and A is pre-exponential constant. It's a constant, basically. And they give you values here of the values in water and in air for the index. And they use different, like they did Austin chalk, which is very common in those areas. Clear Fork and some other sandstones. They tested them with their method. It's a small design. And it basically, but it's a delicate design. Like if you don't get the reading right of the test, dual torsion test, and I cannot even explain it. I don't even know how it works. But what I want to bring to your attention is this relationship here. That is basically dependent on a constant, the stress intensity, and the index. And you can get the index and you can get the index from that test. That's basically what it's giving you. Now, if you have the velocity, and you say that every iteration is like a 1 second time step, and the velocity is 1 feet per second of the fracture growth. You know that in this 1 second, the fracture grew 1 foot, okay? And you can make an adjustment, how much it grew in length and how much it grew in height. And you have the new height and the new length and the new height. You put it onto a PKN pseudo 3D model or a KGD, depending, and you basically have the new fracture geometry, which changes with time, of course. And that's how a model can work. John also had his own model for fracture growth. It was called joints. I think he wrote it during his PhD when he was in Stanford, or a version of that he wrote it when he was in Stanford. And it's a very practical one to use. Actually, it was Excel-based, Visual Basic with Excel. And Donald, when you were in Texas, did you meet John Olson?
Yeah, he took us to a field trip.
Oh, nice. Was he nice to you?
Yes.
I should have told him you know me.
Yeah.
Yeah. Yeah, he's a very nice. All those authors were very good. Anyway, that's about the speed, the propagation velocity. And of course, just something to say again, these tests, they may be very off from reality. So you need to take that into account. It's not like you have to come up with a better test or criticize them. It's more like you need to understand that this is a limitation. Okay, that's the inputs that we can have. That's the inputs we can put in. End of story. Okay, slide number 55. We're almost there. Other well stimulation techniques. We talked in this module about hydraulic fracturing, but this is not the only stimulation technique that we are gonna use, that is available. There is other ones. And I emphasize well stimulation techniques because hydraulic fracturing is a reservoir stimulation technique. You are changing the permeability of the reservoir near the wellbore. But well stimulation techniques are several, and it could be acidizing. Acidizing is also a reservoir stimulation technique, but there is other matrix acidizing is an option. It is not the same as fracturing with acid. And that's why I have this picture here. Fracturing with acid is when I'm injecting acid. It's like I'm doing hydraulic fracturing, but instead of water, I'm using acid. Instead of like ordinary fracturing fluid, I'm using acid. Matrix acidizing is making wormholes in the rock. Okay. Fracturing with acid, I'm trying to do both. And it's many places where hydraulic fracturing is illegal. Fracturing with acid is not. So there was a time when price of oil was high, that people from France were visiting in Texas and they were talking about making hydraulic fractures with CO2. Because if it's CO2, fracturing fluid is not considered hydraulic fracture in the name of the law. So that's, I guess, a funny outcome of those weird legislations. Explosive fracturing, that's like they look back in the old days. It didn't end there, but basically any way without the fluid that you can try to induce tensile fractures is basically explosive fracturing. You can use a torpedo, you can use some sort of sophisticated explosives down the well. You really want stuff that won't leave a lot of debris behind. Because even if the debris is not a lot, it can still clog the fractures back to the well. So you don't want that to happen. So explosive fracturing, that's one way to stimulate your well. But also very important here is gas lift. And you will be surprised, this is something that you learn from production. Gas lift is an artificial lift method. The way it works is that you, long story short, you try to decrease the density of the fluid column inside the well to make it flow easier and get out of the well, get to the surface. Okay. The way they are doing it is considered, for some people, is considered artificial lift method. For some other people, not a lot, it's considered stimulation actually, because you are changing the fluid inside the well. So it's like you are stimulating the well using gas lift. So it's a little bit of a catch here. Yeah, gas lift is, yes, you are assisting fluid to come up the well, but you are also changing its properties. So it's not very different than changing the permeability of the reservoir during hydraulic fracturing. So gas lift is considered as one, could be considered as a stimulation method. And that brings us to the end of module 3. We learned about hydraulic fracture operation basics. We talked about the main parts of a frac spread. We talked about hydraulic fracture geometry modeling. We talked about radial coin-shaped KGD and PKN pseudo 3D. We talk about stress shadowing and limited entry techniques. We talk about hydraulic fracture propagation criterion or criteria and the speed of hydraulic fracture propagation, which is important. We talked about economics of hydraulic fracture treatments. I should say, I shouldn't have A, economics of hydraulic fracture treatments. And yeah, that's a wrap for module 3. Any question for the module 3? Okay. So I guess that's a wrap. Have a nice Easter weekend. I will be available if you want to reach out to me. Send me an email or something for any questions, etc., etc. Homework is due on Monday, 1 minute before midnight. Make sure you submit it. It's an easy homework, easy points to get. And yeah, I mean, we'll carry on Tuesday with module 4. And also, I know I'm moving a little bit faster than what I was, I guess, in the previous years. Seems like it. If you think I went by a certain topic or a subtopic very fast, let me know. And I will go back and do it again or be more explanatory about it so I can make up, you know, if I went by through some sections a little bit too fast. It wasn't intentional, that's for sure. So thank you very much. Have a nice weekend. Happy Easter. And see you on Tuesday. Thank you. Thank you, Donald.
Thank you.
See you.